Hey friends, good morning. This presentation will be all about Euler's theory of long columns. Now, in the previous few lectures we learnt about strut. A strut was effectively a short kind of a compressional member which takes in its load effectively by compression, and for the design of the strut one must ensure that the compressive stresses falling on the strut will be lesser than the compressive strength of the strut. Now, if the strut is made up of concrete, and concrete effectively we know is some sort of a weak material in tension, so what basically happens is that we have to ensure that at every cross section of the strut the internal forces are effectively compressional, right? So to do that, essentially we found out what should be our positioning of the load system so that this condition is satisfied, and we learnt about the concept of the core of the section in which we should position in the load. Right. Now from this lecture I will take up the theory of Euler's long columns. Right. Now what is a long column basically? Now for studying structural analysis, for studying any kind of structures, one must know its failure state, right? How it fails. And effectively maybe it's a column, but a long column effectively doesn't fail by compression, but it fails by buckling, because of the thing we will learn in this lesson. Let us proceed. For example, the bending equation, suppose, right, is like this, wherein if a beam is aligned about x-axis and there are some transverse loads acting, then the beam will effectively deform like this, and this will be the elastic line deflected pattern of the beam. Right. Now suppose let us take 2 points A and B. Now due to bending, let us say that if we draw normal from A and normal to B, the difference of the angle is suppose d theta, and the distance between A and B suppose is nothing but is equal to suppose ds. If I draw a tangent at this point, then effectively this is theta. Now from the bending equation we know effectively that m by ei is nothing but is equal to 1 by r. Right. From here we know this is my radius, right? So r d theta, that is r d theta, is equal to nothing but is equal to ds. Now ds, as it's an elastic curve, therefore ds can be taken to be equal to dx, because there is very small deformation as such, right? So ds can be taken as dx. So I can write this in the form of d theta dx. Now what is this d theta dx? It indicates the change in slope of the elastic curve per unit length, right? And what is this theta? Theta is essentially the change of the displacement in the y direction, that is dy with respect to x, right? So derivative of y with respect to x is theta. So if we put this here, so effectively it will be d2y dx2. So I can rub this, and effectively my relation is m by ei is equal to d2y dx2. Now let us see the sign conventions. Now this is a kind of elastic deflected pattern, and here the bending moment are essentially sagging moments, right? So effectively in this case m is positive, right? Now d theta dx, it's an algebraically decreasing function of x, because this theta, this change of slope per unit length goes on decreasing with x. So it's an algebraically decreasing function of x. Now in case of a hugging moment, we will see some kind of a negative moment, and the hugging moment, that's the shape of the curve will be like this. So it will be some sort of an increasing function of x. So this will be increasing. So effectively we see opposite signs corresponding opposite signs, and essentially I can put this as negative and I can place the normal value of the bending moment. So this is the differential equation of the elastic line. And if we solve this differential equation, then effectively the solution is y is equal to fx, right? I get the equation of this elastic curve, right? And then I can place boundary conditions to this. Now this concept, we are going to utilize it now in case of a long column. Now let us take an example like this, that if suppose this is a column and suppose that this is rooted to the ground, right? Now we apply a force, suppose P. Now the basic theory of long columns is like this, that if I give it some sort of a lateral deflection, suppose the column, I give it some sort of a lateral deflection delta, right? Now at values of P to be lesser than PCR, or the critical load, we will find that the column, when we retract the load, when we take off the load, the column reverts back to its original vertical configuration. So if I give it some sort of a lateral deflection delta and I apply a load P till the point where P is less than PCR, the column will revert back to its vertical configuration once this P is removed, and therefore delta in this case is equal to 0. Now when P is equal to PCR, it's a case of a neutral equilibrium. What basically happens is that if I give it a delta deflection, lateral deflection, and P is equal to PCR, then essentially the column does not revert to its original position, nor it bends indefinitely. So the column just stays there, and this position is called neutral equilibrium position. Now when P is greater than PCR, it's a case of an unstable equilibrium, right? In the fact that if I give it some kind of delta lateral deflection and I place in load, then at P greater than PCR, the column will be essentially unstable and will bend indefinitely. And now the whole focus of this lecture would be to find the value of PCR, or the Euler critical load. And let us see how can we do that. Now, what is PCR? The first thing we got to remember is that we got to assume that this column bends in the form of an elastic line, that is an elastic curve. That this is an elastic curve. Now this is y, suppose, and it is at a distance of, suppose, x, right? So this is my y and this is my plane AB, and it is at a distance of x from the point A, suppose, right? Now if I got to find the equation of this elastic deflected curve, then my differential equation is ready. That is m by EI is equal to minus y double dash. Now what is m? M is nothing but is equal to